72 hours. That's the number that should terrify you. Not because it's how long until help arrives, because it's how long the average American can feed themselves without a functioning stove, a working microwave, or a gas line with pressure in it. 72 hours of cold cans and granola bars before the average household hits a wall. Not a food wall, a cooking wall. You have rice, you have beans, you have oats, pasta, dried lentils, maybe even a 50-pound bag of wheat berries if you've been paying attention. And none of it matters if you can't apply heat to it. Calories you can't cook are decorations. They sit on the shelf looking responsible while you eat peanut butter with a spoon in the dark. I spent 4 months testing every off-grid cooking method I could get my hands on, not reading about them, testing them. Burning fuel, boiling water, timing cook cycles, measuring temperatures with cheap thermometers, and a kitchen scale. 12 methods survived. 12 ways to turn raw ingredients into actual meals when the grid, the gas, and the delivery trucks are all memories. 4 filters. That's how every method got graded. Filter 1. Fuel availability. Can you source or make the fuel when supply chains are dead? If it requires a product with a SKU number and a warehouse somewhere in Ohio, it loses points. If you can walk into a forest, an alley, or a demolished building and find fuel on the ground, it scores. Filter 2. Thermal output. Does it produce enough sustained heat to actually cook a meal? Not warm soup. Cook. Rice needs 20 minutes at a rolling boil. Beans need 90. Bread needs 350 degrees for 40 minutes. If your method can't hit those numbers, it's a kitchen decoration with survival branding. Filter 3. Build complexity. Can you set it up with materials you already have, or can scavenge from a hardware store parking lot? Specialty parts, proprietary components, precision machining, all liabilities. The best methods on this list are built from things most people throw away. Filter 4. Longevity. Does it work on day 1 and day 200? A method that burns through irreplaceable fuel in a week is a sugar rush disguised as a meal plan. We're looking for methods that function indefinitely on renewable inputs. 12 methods, 4 filters. One rule: if you can't cook with it by this weekend using stuff you already own, it doesn't belong on this list. First tier. The emergency shelf. Methods 12 through 9. These work. They'll keep you fed in a blackout, an ice storm, a week without power, but they have ceilings. They're the training wheels of off-grid cooking. Useful, limited, and eventually outgrown. Number 12. The calorie trap. Here's a number that will ruin your emergency kit. A single sterno can produce roughly 4,000 BTUs per hour. Sounds decent till you realize a standard kitchen burner puts out 7,000 to 12,000. You're cooking at half power on a good day. A can of sterno lasts about 2 hours. That means heating, not cooking. Heating, maybe 4 cups of liquid before it's gone. Now open your pantry. Count your sterno cans, divide by 3 meals a day. That's your timeline. For most people, it's measured in days, not weeks. The physics are straightforward. Gel fuel burns at a relatively low temperature, and the flame geometry disperses heat outward instead of concentrating it upward. You lose BTUs to open air on every side. Your pot is getting maybe 40% of what that little blue flame produces. The rest is warming the room, which is nice if you're cold and useless if you're hungry. Sterno has a role: warming, light simmering, emergency tea, keeping a pot from cooling while you sort out a real heat source. But if your entire grid-down cooking plan starts and ends with gel fuel, you're planning to eat cold rice by Thursday. The catch is also the advantage. 3 cans and a cheap folding stove weigh almost nothing and fit in a kitchen drawer. That's not a cooking system. It's a fire insurance policy. Keep 6 cans. Expect nothing more from them. Here's where most preppers fall in love with the wrong promise. Number 11. The beautiful liar. Solar ovens. The concept is seductive. Free fuel, 0 emissions, infinite supply. Point a reflective box at the sun, trap heat, cook dinner with the power of pure optimism and UV radiation. And on a clear July afternoon in Phoenix, it genuinely works. I've hit 350 degrees in a commercial panel-style solar cooker on a cloudless day. Impressive. Almost magical. The problem is, every other day, cloud cover drops output by 40 to 60%. Winter sun angles in northern latitudes cut effective heating in half again. I tested a well-reviewed solar cooker in November in the mid-Atlantic. Peak temperature after 90 minutes of direct sun, 185 degrees. That's pasteurization temperature. That's not cooking temperature. Rice needs a rolling boil, 212 degrees, sustained. Bread needs 350, beans at 185 degrees. Just sit there looking smug while absolutely nothing happens. And here's the part the solar cooking evangelists never lead with. The days you need emergency cooking most, winter storms, prolonged cloud cover, post-hurricane skies, the dark months, are exactly the days solar fails hardest. It's the cruelest irony in off-grid cooking. Maximum need, minimum output. Build one from a cardboard box, reflective tape, and a black pot for under $10. Use it as a supplement on clear days. Treat it as a bonus, not a backbone, because a backbone needs to work in the dark. Now let's talk about something that sounds absolutely ridiculous. I know how this sounds. Stay with me. Number 10. The birthday candle kitchen. Tea candle cooking. 4 tea candles under a metal pot on a simple wire rack. Total cost, about $3. Total foolishness factor. Looks like a Pinterest craft project at the end of the world. Total effectiveness, surprisingly, stubbornly real. 4 standard tea candles produce roughly 300 BTUs combined. Tiny. But here's the mechanism most people miss. Take those 4 candles and confine them under a tight pot inside 2 nested terracotta flower pots. A design sometimes called a terracotta heater. The inner pot traps rising heat. The outer pot insulates it. The air gap between them acts like a thermal buffer. Convective heat recycling. Instead of losing 60% of your BTUs to open air, you're recirculating hot gas across the pot surface multiple times. I boiled 16 ounces of water in 25 minutes with this setup. Not fast, but boiling. A bag of 100 tea candles costs $4 at most and gives you roughly 400 hours of burn time. The math on that is genuinely hard to argue with. It's small batch only, and anything beyond heating water or soup requires the kind of patience that most people lose somewhere around hour 2 of a blackout. This is not a cooking method for a family of 4. It's a cooking method for one person heating 1 mug of broth while the real fire gets built outside. A bridge. A backup to your backup. But for $4, it's the cheapest cooking insurance you'll ever buy. You just made dinner tonight. Something with noodles, maybe, or reheated leftovers. You boiled water, drained it, moved on, didn't think twice. Here's what I want you to remember. Number 9. The invisible oven. Retained heat cooking. You bring a pot to a full boil on any heat source. Fire, sterno, candles, alcohol, whatever you have, then you immediately transfer that pot into a heavily insulated container and let trapped thermal energy finish the job. A towel-wrapped pot inside a cooler, a sleeping bag stuffed around a Dutch oven, a lidded pot buried in hay inside a cardboard box. This technique was standard kitchen practice before gas stoves existed. Your great-grandmother probably knew it. You forgot it. The physics are pure thermodynamics. A well-insulated vessel loses heat slowly enough that food continues cooking at near-boiling temperatures for hours after the flame goes out. The insulation doesn't add heat. It prevents heat from leaving. Same principle as a thermos, scaled up to pot size. I boiled a pot of lentils for 5 minutes on an open flame, transferred it into a cooler packed with old towels, and came back 3 hours later, fully cooked. Texture perfect. No additional fuel burned after that initial 5 minutes. The brilliance is fuel economy. Whatever heat source you're using, retained heat cooking cuts your fuel consumption by 60 to 80%. That's not a number I read somewhere. That's a number I measured with a timer and a fuel scale over 2 weeks of testing different insulation setups. A sleeping bag scored highest. Hay bales were a close second. The limitation is honest. Retained heat only works for foods that cook by sustained simmering. Stews, grains, legumes, soups, porridges. You can't fry an egg with retained heat. You can't bake. You can't sear a piece of meat. But if your primary grid-down diet is beans, rice, and oats, and if you've done your food storage homework, it is. This method stretches every other method on this list 2 to 4 times further. That's not an improvement. That's a multiplier, second tier. The hard and middle, methods 8 through 5. These are not backups anymore. These are real cooking systems. Full meals, sustained heat, serious capability. If you have one of these dialed in, you're not just surviving a power outage. You're eating well through one. The ultralight backpacking community figured something out decades ago that most preppers still haven't absorbed. Number 8. The Pocket Inferno. Alcohol stoves. A cat food can with holes punched around the rim, filled with denatured alcohol or isopropyl. Total weight under 2 ounces. Total construction time, 4 minutes in my driveway with a hole punch. A utility knife, and an empty Fancy Feast can. Boils 16 ounces of water in about 8 minutes. The fuel is the interesting part. Denatured alcohol is sold at every hardware store in America. Isopropyl is in every pharmacy, every grocery store, every gas station. In a genuine pinch, high-proof grain alcohol works too. Yes, the drinking kind, which makes it the only cooking fuel you can also toast the apocalypse with. And alcohol burns clean. No soot, minimal carbon monoxide compared to wood, and the flame is easily controlled by covering the burner with a coin or flat metal piece. The catch: BTU output per ounce of fuel is about 60% of white gas and roughly 40% of propane. You're trading raw efficiency for availability and simplicity. A quart of denatured alcohol gives you around 10 to 12 full boils. Sounds fine until you calculate a family of 4 3 meals a day, over a month. You'd need 5 gallons. That's not impossible to stockpile, but it's also not trivial. Pair this with retained heat cooking from number 9, and you cut that fuel requirement in half. Boil with alcohol, transfer to insulation, let physics finish the work. Systems thinking, that's the real skill here. The stove fits in a jacket pocket. The fuel fits under a bathroom sink. The knowledge fits between your ears forever. You walk past it every weekend and never think about it as survival equipment. Number 7. The Suburban Reactor, your charcoal grill. Already sitting on your patio or deck, already paid for, already understood by almost every adult in the country, and massively, criminally underestimated as a grid-down cooking platform. A standard 22-inch kettle grill with the lid closed is a convection oven, not a metaphor, not an exaggeration. It literally functions as one. Close the lid, control the bottom and top vents, and you can hold 350 degrees for over an hour on 30 briquettes. That's bread temperature. That's casserole temperature. That's roasting temperature. Most people use their grill as an open flame char machine. Lid up, burgers sizzling, smoke everywhere. That's like using a pickup truck only in first gear. The lid is the technology. Airflow control through the vents is the skill. Airflow control through the vents is the skill. 20 pounds of charcoal gives you roughly 15 to 20 full cooking sessions depending on what you're making. And here's the detail people forget. Charcoal stores almost indefinitely if you keep it dry. That bag in your garage from 3 summers ago, the one behind the lawn chairs, it works fine. Moisture is the only enemy. A sealed plastic bin solves it. The weakness is obvious and real. Charcoal is a manufactured product. When your supply runs out, you can't walk into a forest and find more. Unless you learn to make your own from hardwood, which is entirely possible, but requires a separate skill set and a fair amount of labor. A 40-pound bag of briquettes costs about $15. Buy 4 bags. Store them in sealed bins in a dry spot. You just purchased roughly 2 months of full cooking capability for $60. That's cheaper than one panic run to Costco. Do it this weekend. We're stepping up now. Everything from here forward uses fuel you can find in a ditch, a backyard, or a pile of demolition debris. In East Africa, there's a cooking tool that has saved more lives than any piece of survival gear you've ever seen, reviewed on this platform. Number 6. The Kelly Kettle, or any chimney-based water heater, built on the same principle. The concept is ancient and borderline unfair in its efficiency. A double-walled metal cylinder with a hollow center. You build a tiny fire in the base using whatever scraps you can find, and flames draw upward through the chimney center, heating the water jacket that surrounds it on all sides. A Kelly Kettle boils 50 ounces of water in 3 to 5 minutes, using nothing but a handful of twigs, pine cones, bark scraps, and dry leaves. Let me say that again. 3 minutes. With twigs. The thermal efficiency is staggering. Somewhere around 80 to 90% of the heat energy transfers directly to the water because the flame is completely enclosed by the vessel. Compare that to an open campfire where you're losing 85% of heat to open air, and you start to understand why humanitarian engineers fell in love with chimney designs. The limitation is real. A Kelly Kettle is primarily a water boiler. You can cook on the cap or add a pot support accessory, but it's not designed for slow simmering, stewing, or baking. It does one thing brilliantly, and that one thing is making boiling water almost trivially easy. With almost no fuel. Pair it with retained heat cooking from number 9, and suddenly you have a complete cooking system. Transfer to an insulated vessel. Let thermodynamics do the rest. Dinner is done. The commercial versions run $60 to $90, but the underlying principle can be replicated with nested tin cans and basic metalwork. That's your Monday project. 2 cans, a tin snip, and an afternoon. Not a campfire. Not a fire pit, not a pile of sticks on the ground where you balance a pot on 2 rocks and pray for the wind to stop. Number 5. The invisible fire, the Dakota fire hole. 2 holes in the ground, about a foot apart, connected by a tunnel at the bottom. One hole is the fire chamber, the other is the air intake. That's the entire design. The most tactically sound cooking method in human history, used by the Lakota and other Plains nations for centuries, and still taught in every serious military survival course on the planet. Here's why it works. The air intake tunnel creates a forced draft feed. Cool air gets pulled underground into the base of the fire. This accelerated airflow means the fire burns hotter, faster, and cleaner than any surface fire with the same fuel, which means wind can't reach or cook fire, and the visual signature from a distance drops to almost nothing. No towering flame. No smoke column catching light. You can cook a full meal 200 feet from a road and nobody sees it. But the mechanism most people miss is the heat efficiency gain. Because the fire sits in a hole, nearly all the radiant heat travels directly upward into the pot sitting across the top. An open surface fire wastes 80 to 85% of its thermal energy to open air. A Dakota hole recaptures 40 to 50%. That's a massive jump for a technology that requires nothing but a stick and the willingness to dig. The catch: you need diggable soil. Rocky ground stops you cold. Frozen ground in winter is a no-go without serious tools. High water tables flood the hole. Clay-heavy soil works but takes longer and dulls your tools. Sandy soil is ideal for digging but collapses without reinforcement. I've built these in heavy loam in about 15 minutes with a camp shovel. In packed red clay, it took closer to 40 minutes in a vocabulary I won't repeat here. Go outside this weekend and dig one. Seriously. Even if you never need it for cooking, the knowledge of how your local soil behaves when you put a shovel in it will teach you more about your immediate environment than any survival book on your shelf. Let me pause here, because I know what some of you are thinking. You're thinking you don't need to know 12 methods. You're thinking you'll just build a campfire if things go bad. Maybe roast some hot dogs on a stick like summer camp. And that thinking, that exact lazy assumption, is what separates people who eat from people who burn through their fuel supply in 4 days and wonder what happened. A campfire is the least fuel efficient, most exposed, hardest to control cooking method that exists. It works the same way a house fire works, by being wildly wasteful with energy and hoping some of it accidentally does something useful. Every method above number 5 on this list exists because someone, somewhere, usually someone who was actually starving, figured out how to take the same chemical reaction, combustion, and focus it, contain it, direct it. The difference between a campfire and a rocket stove is the difference between a garden hose and a pressure washer. Same water, radically different results. If your entire cooking plan is I'll just make a fire, you're planning to burn 3 times the fuel, take twice as long, and announce your position to everyone within a half mile. That's not a plan. That's a habit, wearing a flannel shirt. Final tier, the permanent kitchen. Methods 4 through 1. These aren't emergency measures anymore. These are civilization rebuilding tools. Every method in this tier runs indefinitely on fuel you harvest from the landscape around you. And every one has been field-proven across centuries and continents. If you only master 4 cooking methods for the rest of your life, make it these 4. Now we go underground, literally. Number 4, the time machine. Earth oven cooking. Dig a pit about 2 feet deep and 3 feet wide. Build a hardwood fire in it. Heat dense rocks in the fire for 1 to 2 hours. Lay your food on the hot rocks, wrapped in wet leaves or cloth. Cover everything with dirt. Walk away. Come back in 4 to 8 hours. Dinner is done, and it's been done for a while. This is the oldest cooking technology on Earth. It predates pottery. It predates metal. It predates agriculture. Humans were pit-cooking mammoths before they figured out farming, which says something about our species' priorities that I find deeply relatable. The thermal physics are extraordinary. The ground itself is a near-perfect insulator. The ground itself is a near-perfect insulator. A properly loaded earth oven holds temperatures between 200 and 400 degrees for 6 to 8 hours using rocks heated once. 1 fuel load. 1 fire. An entire day's cooking for a large group. The mechanism is thermal mass. Dense rocks, river stones, basalt, granite, absorb enormous amounts of heat energy per pound and release it slowly over hours. The surrounding earth prevents that stored energy from radiating away. You're essentially baking food inside a geological slow-release battery. I cooked a 4-pound pork shoulder in a pit oven for 6 hours. Internal meat temperature hit 195. It fell apart at the touch of a fork. The catch is time. This is not a method for someone who wants dinner in 30 minutes. This is a method for someone who plans meals the way a farmer plans seasons, hours, or days ahead. And you absolutely need to know your rocks. Limestone can explode when heated rapidly. Wet river rocks can shatter with enough force to send fragments several feet. Porous volcanic rock holds trapped moisture that turns to steam under heat. Pressure plus containment equals shrapnel. Use dense, dry, solid stones. Tap 2 together. If they ring like ceramic, they're dense enough. If they thud like clay, pick different rocks. This is not optional knowledge. It's the difference between dinner and a trip to the emergency room. Let's talk about the most underrated cooking surface in human existence. Number 3, the inheritance. Cast iron over an open hardwood fire. I know what you're thinking. This is just a campfire with a nicer pan. It's not. The difference is the metal, and the difference is physics. Cast iron has a thermal conductivity of about 52 watts per meter Kelvin. That's lower than steel, lower than aluminum, lower than copper. And that's exactly why it works for cooking over unpredictable heat sources. Low conductivity means cast iron heats slowly and somewhat unevenly, but it holds heat like a vault door. It maintains that temperature even when you add cold food, drop in wet batter, or shift it 6 inches away from the flame. Every other material drops in temperature the moment you load it. Thin stainless steel warps because uneven thermal expansion buckles thin-gauge metal under direct flame. Aluminum heats and cools too fast, creating a cycle of scorching and undercooking that drives you insane. Cast iron absorbs the chaos of an open fire and outputs steady, consistent, workable heat. That's not campfire romance. That's material science earning its keep. And here's the fact that separates cast iron from every other cooking tool on Earth. It doesn't wear out. It doesn't corrode if you maintain the seasoning. A skillet manufactured in 1920 performs identically to one made last Tuesday. In a long-term grid-down scenario, cast iron is the only cooking tool that literally never needs replacing. Everything else degrades. Non-stick coatings flake. Thin steel rusts through. Aluminum fatigues and develops hot spots. Cast iron just sits there, decade after decade, getting better with use because each cooking session adds another molecular layer of polymerized oil to the cooking surface. The pan improves by being used. Name another piece of survival equipment that does that. The limitation: weight. A 12-inch lodge skillet weighs 8 pounds. Not backpack friendly, but if you're cooking at a fixed location, and in any sustained disruption longer than a few weeks, you will be. Weight is completely irrelevant. Get a 12-inch skillet, a 10-inch skillet, and a 5-quart Dutch oven. Total cost under $80 at any outdoors retailer. That's a lifetime of cooking capability that outlives you and works on every single heat source in this entire countdown. Number 2 is where engineering meets desperation, and it works better than it has any right to. Number 2. The scavenger's turbine. Wood gasifier stoves. This is the method that should be famous and somehow isn't. A wood gasifier doesn't just burn wood, it burns the gas that wood produces when it's heated. 2 nested cans, a smaller one with holes punched at the bottom sitting inside a larger one with holes at the top. It undergoes pyrolysis, releasing volatile gases: hydrogen, carbon monoxide, methane. Those gases rise through the gap between the walls, mix with secondary air flowing in through the outer holes, and ignite at the top rim. A clean, hot, nearly smokeless flame. A gasifier running on dry twigs and wood chips produces temperatures that rival a propane burner. I measured over 900 degrees Fahrenheit at the pot surface on a gasifier I built from 2 tin cans in my garage in 20 minutes, with a hole punch and a pair of tin snips. Total material cost: whatever I pulled out of the recycling bin. The thermal efficiency lands between 35 and 50%, which is 3 to 4 times better than an open fire. But the fuel consumption is where this thing becomes almost absurd. A handful of dry sticks the diameter of your finger will cook a full meal. You could cook 3 meals a day for a month on what falls off a single mature tree in one windstorm. Think about that. 1 tree, 1 storm, a month of cooking fuel lying on the ground. And because you're burning gas rather than solid wood, the smoke output drops to nearly zero once the secondary combustion kicks in. Low smoke means low visual signature, less respiratory damage to your lungs, and less creosote buildup on your cookware. In a long-term scenario where you're cooking indoors or under shelter, that smoke reduction isn't a convenience, it's a health issue. Indoor air pollution from open fires kills nearly 4 million people per year, globally. The gasifier sidesteps that. The catches are real. Gasifiers need dry fuel. Damp wood chokes the pyrolysis process and kills the secondary burn, leaving you with a smoky, inefficient mess. In wet climates or extended rainy seasons, you need a fuel drying strategy. A covered rack near your shelter, a warm storage nook, a rotation system where tomorrow's fuel dries while today's fuel burns. And the flame is difficult to throttle. A gasifier runs hot or it dies. Simmering is tricky without raising the pot height or improvising a heat diffuser. But the build is the beautiful part. 2 cans, a hole punch, 20 minutes, no welding, no special tools, no purchased parts. You can build one from the debris of a collapsed building. Let that settle for a second. The ability to cook a hot meal from rubble and twigs with the stove you fabricated from garbage in under an hour. That's not prepping. That's engineering resilience directly into your nervous system. Number 1, we've been building toward this the entire time. Every method above is either limited by fuel supply, limited by weather, limited by thermal output, or limited by construction complexity. This one has essentially no ceiling. Number 1, the forever engine. The rocket stove. 16 bricks. That's the entire materials list. 16 standard bricks or cinder blocks, stacked in an L-shaped configuration. A horizontal feed tube meeting a vertical combustion chamber creates a cooking device so thermally efficient that it changed international humanitarian aid strategy worldwide. The physics are elegant and brutal. The horizontal feed tube allows you to push sticks in gradually, giving you precise control over fuel rate and burn intensity. The vertical chimney creates a powerful natural draft that accelerates air across the burning tips of the fuel, routinely exceeding 1,100 degrees Fahrenheit at the flame point. But here's the mechanism that actually matters. The insulated chimney forces hot combustion gas to travel vertically in a concentrated column before hitting the pot, instead of the dispersed chaotic heat cloud of a campfire. You're focusing thermal energy the way a lens focuses light. Same fire, radically different delivery. The result: a rocket stove uses 60 to 80% less fuel than an open fire to cook the same meal. Let that number breathe for a second. 60 to 80%. That means the woodpile that lasts your neighbor 1 week lasts you a month. I built one in my yard from salvaged cinder blocks and a piece of scrap angle iron for a pot rest. Total construction time, 12 minutes. Total cost, 0. Because I pulled the blocks from a demolished retaining wall down the street. I boiled a gallon of water in 11 minutes, burning sticks I snapped off a dead branch hanging over my fence. Sticks the thickness of my thumb, beans and fried eggs on it over 3 consecutive days using fuel I gathered on 10-minute walks around my neighborhood. Not the woods, not state land. My suburban neighborhood, dead branches and park strips, fallen twigs along fence lines, snapped limbs after a Tuesday windstorm. The fuel requirement is the revelation that makes everything else on this list feel like a warm-up act. A rocket stove burns sticks. Not logs, not split firewood, not manufactured charcoal briquettes. Sticks, material that exists in virtually every environment on Earth. Urban, suburban, rural, wilderness. Material that no one is stockpiling or competing for. Material that regenerates every single year. Material that a 10-year-old can gather in 15 minutes. Walk outside right now. Look at the ground under any tree on your block. See that? That's not yard waste. That's fuel. Not for a week. Not for a month. For years. The humanitarian record is what pushes this to number 1 and keeps it there. Rocket stoves didn't emerge from the prepper community or the bushcraft YouTube circuit. They came from international development engineers trying to solve a specific crisis: indoor air pollution deaths in sub-Saharan Africa. Nearly 4 million people per year dying from cooking over open fires in enclosed spaces. The rocket stove design reduced fuel consumption by up to 80% and smoke output by over 90%. It's been deployed in refugee camps across Kenya, earthquake response zones in Haiti, displacement sites in Syria and South Sudan. Not as a pilot program, not as an experiment, as standard infrastructure. When the United Nations and the World Food Program need to feed displaced populations with minimal fuel and zero functioning supply chain, they build rocket stoves. That's not a product review. That's a field-tested survival record spanning decades, continents, and the worst conditions human beings endure. The permanent version uses fibric or rammed earth insulation around the combustion chamber, which increases efficiency even further by preventing heat loss through the walls. You can build a permanent rocket stove into an outdoor kitchen using nothing but earth, clay, and salvaged brick that have been running daily for over 10 years with zero maintenance beyond sweeping ash. Add a plancha, a flat steel griddle surface, over the top, and you can cook tortillas, pancakes, eggs, and stir-fry on one side, while simultaneously heating a pot of water on the chimney exit. One fire, 2 cooking surfaces, twigs as fuel. The catches exist and deserve honesty. Like the gasifier, rocket stoves want dry fuel. Wet sticks smolder, choke the draft, and fill the chimney with smoke instead of clean combustion gas. You need a covered fuel storage area or a drying rack, which means thinking about fuel supply the way you think about food supply. Planning ahead, rotating stock. The concentrated heat jet also makes low-temperature simmering difficult without raising the pot or inserting a diffuser plate. And a proper permanent build, the kind that lasts a decade, takes a few hours of labor and some understanding of thermal mass and insulation principles. But those are engineering problems, not survival problems. A challenge you solve with bricks, clay, and a Saturday afternoon is not a real obstacle. It's a project. 16 bricks, dead sticks from your yard, a permanent cooking system that runs on landscape debris, produces near-zero smoke, uses 80% less fuel than the campfire your neighbor is struggling with, and has been proven in the worst conditions on the planet by the organizations whose entire job is feeding people when everything else has already failed. That's not the top of a list. That's the foundation. Everything else on the list was leading to. Every other method in this countdown is something you use until you build this one. 12 methods, 4 filters. One question: when the power goes out tonight, not next year, not in some hypothetical collapse scenario you daydream about, tonight, can you feed your family a hot meal? If the answer isn't an immediate and specific yes, you have work to do this weekend. Not research, not planning, not adding items to a wish list. Work. Pick one method from this list. Build it, buy it, or dig it before Sunday. Then pick a second that covers the first one's weakness. 2 methods. Redundancy. That's the system. The grid doesn't send a warning before it fails. Neither should your kitchen.